In the last video, we derived the Boltzmann equation, or the Boltzmann distribution here, which I don't know how it appears to everybody. It looks a little bit complicated and a little bit abstract, but the way to understand any kind of basic result like this is always to do a nice illustrative example. So that's what we're going to do next. We're going to look at how this Boltzmann distribution applies to a two-level quantum system. Most of the time up to now I've been talking about classical systems, but everything that's been said so far applies just as much to quantum systems as to classical ones. And at this point, the quantum systems are actually easier to deal with, easier to understand than the classical systems are. And so we're going to do a quantum system. All right, so here's the system we're going to consider. It's got a T-bath, of course, that's the surroundings. And those surroundings are assumed to be weakly coupled to our system, but inside the system there's just a something. Exactly what it is, well, we don't specify, but whatever that something is, it has only two states, two quantum states, each with its own energy. Quantum state 0 with energy E0 and quantum state 1 with energy E1. One practical way to realize a two-state system like that is to consider a single spin in a magnetic field. So here I have a magnetic field, and that magnetic field is acting on this single spin, say in the middle of, say, a spin 1/2 proton in a hydrogen nucleus. And when the spin is up and aligned with the field, it has low energy. When the spin is down and aligned against the field, it has high energy. But a spin 1/2 only has two possible quantum states, and so that's it. That's all there is. And so the low energy in this case is this lower state, and the high energy is this upper state. That's a two-level system. Another one, not truly two-level, but approximately two-level, is if you have a molecule, say, dissolved in solution, that has a ground state and a first excited state, and then, of course, all molecules have higher states, but let's suppose those are far away in energy, then the molecule also behaves roughly like a two-state system. And so even something as complicated as a molecule and as close to things of interest to chemists as a molecule behaves at least roughly like a two-state system. So we're looking at a system that, even the two-state system, is of enormous application in a lot of areas of, well, physics and chemistry. All right. So we want to apply the Boltzmann distribution here. That's our general formula. In order to use the formula, the very first thing you want to do is calculate Q, this denominator. The denominator is the sum over all microstates of the system, but there's only two microstates in this system, so the sum just has two terms. It's really simple. It's e to the minus beta energy for state number 0, e to the plus e to the minus beta energy for state number 1. So that's easy. Then, once we've got Q, we just have to make sure we're putting up on top the thing that matches to the probability we want. So if we want the probability of state 0, we put e to the minus beta E0 on top and divide it by Q. If we want the probability for state 1, then we put we put e to the minus beta E1 and divide by Q. So if E0 is a small number, let's suppose E0 is equal to 0, for example, then this would just be 1 over Q, and that's at least probably a bigger number than this number over here. We'd have a certain amount of population in the ground state, a certain amount of population in the upper state, and these two formulas would allow us to calculate what those populations are. Let's see how that works. First of all, it will be useful to simplify these two formulas by one step. What I'm going to do is take this formula for P0, and I'm going to multiply it on the top by e to the beta E0, and on the bottom by e to the beta E0. That's a 1, right? So I'm just multiplying by 1. That doesn't change anything, so that's always possible. If I multiply by e to the plus beta E0 here, that cancels the e to the minus beta E0, and I just get a 1 on top. When I multiply on the bottom by the same thing, the e to the plus beta E0 cancels this first term, and it gives me an e to the minus beta delta E on the bottom, where delta E is the energy difference between the ground state and the first excited state. So in the end, this probability doesn't depend on the absolute value of the ground state energy and the absolute value of the excited state energy. It only depends on the energy difference between those two levels, and we're going to find out that that's always true. Even if I had a more complicated system, the probabilities only depend on energy differences, not on absolute energies. And the same thing now turns out to be true if I do the same trick on probability for state 1, and you get e to the minus beta delta E over 1 plus e to the minus beta delta E. All right, so those are our two formulas that we're now going to use. Let's plug some values in and see what we get. Let's first of all look at what those two probabilities are as t goes to 0. If t goes to 0, we're going to absolute 0 of temperature. That means there's no available thermal energy in the surroundings. That means there's no energy for the system to suck out of the surroundings. That means it should be impossible to get to the excited state. And look at the probabilities you get. For P0, if I plug in a value of t equals 0, that means the value of beta, which is 1 over kt, remember. When that goes to 0, beta goes to infinity. That means you're putting an infinity in there. That means this whole quantity goes to 0, and that means the ground state probability becomes 1. The excited state probability goes to 0. So indeed, in agreement with what we expect, when you're at 0 temperature, you're frozen into the ground state. You cannot reach even the smallest of excited states. There is no probability of being in the excited state. All right. And I'm just saying the same things here that I just said. When kt is really small, especially if it goes all the way to 0, then there's no energy available to get to the excited state, and everything is frozen into the ground state. All right, let's try the opposite extreme. Let's take the case where t goes to infinity. In that case, beta, which is again 1 over kt, now that's going to infinity. That means beta is going to 0. That means we're putting a 0 in there, which means we're getting e to the 0, which is a 1. That means this denominator is now 1 plus 1, which is 2. And so the probability for finding the system at infinite energy, at infinite temperature, the probability for finding the system in the ground state is a half. It doesn't go to 0, it just goes to a half. But that's the same probability as for the first excited state. Now, if beta is 0, this is a 1 up on top, that's a 1 down there, and again we get 1/2 for the probability of the excited state. At infinite temperature, the probability of both states are equal and equal to a half. And so the sort of intuitive picture of that is that now you've got a whole load of thermal energy in the background. It's easy to pull some energy in from the surroundings in order to excite your system up to the ground state. And that means that this energy gap between the two is negligible compared to the available thermal energy, and so both probabilities are equal. The system plus surroundings basically just ignores the energy gap now. There's so much thermal energy available, you can just ignore the energy gap. All right, so those are the two limits. That's kind of what you'd expect from both limits. What about some point in between? Let's suppose that we choose the temperature to be equal to the energy gap itself divided by Kb. Kb has units that turn energies into temperatures, and so this whole thing has units of Kelvin and is therefore a temperature. If we plug e to the minus beta delta E, and we put delta E over Kb into here, if we write e to the minus delta E over kBt, and then we put T is equal to delta E over kB, you can see all this just becomes 1, and we get, for the ground state probability, we just get 1 plus e to the minus 1. For the excited state probability, we get e to the minus 1 over 1 plus e to the minus 1. If you put the numbers into that, that turns out to be about 73% and about 27% for the ground state. And so now we're at a situation where we're getting similar but somewhat different probabilities or populations for both the excited state and the ground state. Now Kb, the thermal energy, is equal to the energy gap. And so there's energy enough available to promote the system from the ground state up to the excited state. But it costs you something to do that. And so the probability of being in the excited state is only about a half, or a little bit over a half, 2.5 times greater than the probability of, less actually than being in the probability of the ground, than being in the ground state. All right, here I plotted now the probability of being in the ground state and the probability of being in the first excited state as a function of temperature, really, right? I've got these extra quantities in there, but that's just scaling. That's just normalizing the temperature, in effect. And you can see that as the temperature gets large, so as kT over delta E gets to be about 6 or so, that's enough so that the energy gap between the two states doesn't matter anymore, and both probabilities are starting to get close to a half each. If we were to go further out with the graph here, these would continue to converge until they're both equal, as close as you like, to a half. On the other hand, if you're at low temperature down here, where temperature near 0, then indeed you have frozen the system entirely into the ground state, and the probability of finding it, the system in the excited state is 0. Notice that it takes a little bit of energy, takes a little bit of temperature before you start getting any appreciable probability in the excited state. The excited state has a low region here where it takes a little bit of temperature to even turn itself on. That's the energy necessary to get somewhere in the vicinity of thermal energy equal to delta E. The energy gap that's present in the system prevents any population at all at really low temperatures. All right, a few comments, a few general comments. The first thing is that all of these results we've seen in this example are typical for all systems in the Boltzmann distribution. It's always true that when you're at low T, you freeze everything into the lowest available state, or sometimes there's more than one available state, you freeze it down into all of them then. But whatever the lowest possible set of states is for the system, you always freeze into those when you go to lower temperature. You're basically eliminating all possibility of exciting the system to anything higher than the ground state. If you're at some kind of medium temperature, then things spread out. You've got a few states here. You start getting some population in the excited states, but the higher the energy of the excited states are, the smaller the population gets. Rapidly, actually, because it's an exponential dependence, remember. And finally, if you're at high enough temperature so that there's way more thermal energy than there is the highest energy you need, then you spread the system out entirely, and all the states have equal population. So, for example, for equally spaced states, so for a harmonic oscillator, remember from last semester, harmonic oscillator has equally spaced quantum states. Then when you're at low temperature, everything's frozen into the ground state. When you're at intermediate temperature, things are spread out, but the populations diminish as you go to higher and higher states. And finally, only when you're at really high temperature does everything spread out, and you have basically equal probability in all states. All right. Second comment. This exponential that appears in e to the in p sub I, e to the minus beta e sub I, which is equal to e to the minus e sub I over kt, remember? That comes, remember, from the derivation. That came from the surroundings. It came from W sur. So this is not a property of the system. It's a property of the surroundings, and it's accounting for entropy changes in the surroundings, or if you like, it's counting for changes in the number of microstates in the surroundings, and all this text is just saying that. When you pump energy into the system from the surroundings, you're reducing the energy of the surroundings. According to this, that greatly reduces the number of microstates available to the surroundings, and this exponential factor accounts for that. On the other hand, if you send energy out of the system into the surroundings, then the opposite happens. You're increasing the number of microstates available to the surroundings. And again, this same term accounts for that too. I said this already, I said this in the derivation, but let me emphasize it here, that anytime your system has more than one microstate at the same energy, so here we've got degeneracy in our quantum system, then all the states at that same energy also have the same probability. Again, it's the ergodic hypothesis showing up. This system isn't isolated. It doesn't obey the ergodic hypothesis on its own, but every little subsystem of states that has the same energy still obeys the ergodic hypothesis. If some set of states in your system all have the same energy, then they all have the same probability. Finally, I made some of these points before already, but let me just remake them here because it's important. The thing that matters, the thing that controls the probability, isn't the energy per se, it's the energy in units of the local available thermal energy, kBT or KT. Effectively, KT sets the scale for what energies are important in your system. If KT is much smaller than E sub I, then E sub I is a big energy. It's an important energy. If kBT is about the same size as E sub I, then E sub I is a medium energy. And if kBT is much bigger than E sub I, then E sub I is basically negligible. It's a small energy and doesn't do much one way or the other. So here's that illustrated again. Here's our two here's our two microstates, state 1, or state 3 microstates in this case, I guess. State 1, state 0, state 2. Two of them are very close together, and I've got thermal energy that's much bigger than this energy gap. Then this energy gap just isn't going to matter. Both of these guys are going to have very similar probabilities or populations, and state 2 here is going to have a much smaller probability or population. On the other hand, if I lower the temperature so that now kBT is smaller than this energy gap, then all of a sudden this energy gap matters, and the population of state 0 will be much bigger than the population of state 1 in this case, and the population of state 2 will be almost negligible. All right. Before we go, let me just do one quick calculation. Remember that kBT, that Kb is just equal to the gas constant R divided by Avogadro's number. And so we can express this available thermal energy either in microscopic units, units appropriate for a single molecule or a single atom or a small number of atoms or molecules. In that case, the quantity kBT, when we're at 298 K, is about 4.1 times 10 to the minus 21 joules, or in somewhat nicer units, 4.1 piconewton nanometers. If you don't like piconewton nanometer units, that's okay. They are a little unusual for chemists. But single molecule people love those units, so you may see them more and more as time goes by. On the other hand, if you're talking about a mole of things, so these are macroscopic units, then the quantity that matters is RT. That's just Avogadro's number times kBT. And that's our number that we've already used widely in this class, 2479, about 2,500 joules per mole. All right, we'll pick up the next topic next time.